Hey everyone, I'm Miguel and I have a special guest to talk about integrals today. I have Dr. PK from PK Math. He has a YouTube channel, he has an Instagram, and he has a TikTok where he talks about amazing and pretty fun math problems that you can just find challenging and, make your day a little better. So PK, thanks so much for being here, man. I'm so happy to collaborate.
Thank you, Miguel. Yeah, I actually started to here.
Awesome. So he already covered an integral using the Feynman technique, which is exactly what I'm going to go ahead and do. So feel free and go watch his video on his channel. I'll make sure to link it in the description below. Guys, what we have here is an exciting integral that is going to include the Feynman technique. And you already know that I'm a sucker for those things. So we're definitely going to have some fun. This problem is going to have the Euler formula. It's going to have obviously some basic integration techniques. And at the end, it's a little technical, but it's going to be fun. So let's go ahead and get started. So we have the integral from 0 to infinity of 1 minus cosine of x over x e to the x with respect to x. And if I want to go ahead and do this using the Feynman technique, I'm first going to go ahead and approach the Euler formula because we have e to the ix is equal to cosine x plus I sine x. And I really love this because it's going to convert my cosine in terms of e, and that's actually what I want. And the way this works is, let's just say, for example, I'm already going to go ahead and establish my alpha for the Feynman technique. I'm going to go ahead and make my input alpha x. So I have cosine of alpha x plus I sine of alpha x. And this is perfect because with the Euler formula, you're able to call for the real part of this solution here. So if I were to just ask for the real part of e to the I alpha x, that's just going to give me the cosine of alpha x. And that's exactly what I want. So now I'm going to go ahead and start creating my equation so that I can go ahead and implement the Feynman technique. So let's just say, for example, I love doing f of alpha, and I'm going to make this equal to the real part of the entire integral from 0 to infinity of 1 minus e to the I alpha x all over x e to the x, okay? And again, this right here was technically the Euler formula up here, or the Euler components. But when I take the real part, this is really just the cosine. That's exactly what I want. Now, whenever you do the Feynman technique, it's really difficult because you have to establish some ground rules. I like to say you need something, or I'm sorry, you know something, you need something, and we're going to find something. This already helps me just understand what I'm going to do as I go through the problem. So one thing that we're going to know is that if we were to plug in f of 0, in other words, your alpha is equal to 0, this will make e to the 0. Now, e to the 0 is 1, so we have 1 minus 1 on the numerator, making this entire integral 0, and that's actually really nice. Now, what we need to solve this integral. In other words, if we make alpha equal to 1, we will have e to the ix, giving us just the cosine of x. So we want f of 1, and that means that we need to find the integral from 0 to 1 of f prime of alpha d alpha, and that, according to the first fundamental theorem of calculus, is equal to the antiderivative of f prime, which is just f1 minus f of f0. But we already know f of 0 is 0. So we're good to go. All right. So now that we established all this, we're going to go ahead and take the partial derivative with respect to alpha. Now, it's very technical, and Dr. PK would agree with you that there's a lot of things that you have to take into account if you want to take the partial derivative of this integral. In other words, move the partial derivative inside the integral sign. And it's all about the functions being bounded. I think there's a nice theorem to that. But just to keep in mind that if we're going to take the derivative with respect to alpha, we're going to treat every variable like a constant. So in other words, we're just simply worried about taking the derivative of e to the I alpha x because all these are constants here. So let's go ahead and take the derivative. I'm going to do it down here. So we are going to have f prime of alpha, and we still have the real part of the integral from 0 to infinity. And now when I take the derivative of the top here, this is 0 minus, and I have minus e, and then I'm going to have, I'm going to have I x e to the I alpha x. I almost forgot what I was doing here. Over, this is a constant, so I just leave it as x e to the x dx. Let's go ahead and write the dx here and close the parentheses. Now, notice that the x's cancel out, or if they simplify, it becomes 1. And that's actually what we want. We wanted to do this so that we can go ahead and create a nice solution to this integral. So what do we get? Before I rewrite this, or as I'm going to rewrite this, notice that I have two e's on the top and bottom. And that's actually by design. I wanted to do this on purpose because I'm going to use properties of exponents to subtract these things. So now what I'm going to go ahead and get is I have f prime of alpha is equal to the real part. And now I'm going to go ahead and just take out this negative I that's on the outside, or I'm going to take it on the outside, integral from 0 to infinity. And now I'm going to have e to the I alpha x minus x. And again, what I did here is that I just used properties of exponents. Now, up here, I want to go ahead and just factor out a negative x. So if I factor out a negative x, this will become 1 minus I alpha. And now we can go ahead and start integrating because we simply just have a function of e to the x. I mean, we know how to do this using some u substitution. This is where I encourage you to try to write these things on your own. But I have negative I, and this will become e to the negative x 1 minus I alpha over negative 1 minus I alpha. I have to make sure that if you're basically doing u substitution, you have to go ahead and include or integrate this correctly. And this is the technical part. Okay, and I'm integrating from 0 to infinity. Now, I don't know if PK, you're already noticing, but I have the bounds at infinity. Typically, we like to put a limit, right? But we all know sometimes we just get a little lazy, so we don't want to plug that in.
Yeah.
So as we do this, when I plug in infinity, or really I'm approaching infinity, this entire value is going to become e to the negative infinity, which is going to approach 0. So this so far still gives me the real part of I have negative I times I have 0 and then minus, and then I have this 0 that I'm plugging in here. E to the 0 is 1. So I have 1 over this entire thing. In other words, 1 plus 1 over 1 minus I alpha. Ooh, there you go. And I'm just going to go ahead. I guess I didn't need the brackets here. Now, if I continue, I have the real part, and I'm going to go ahead and just now simplify this as negative I over 1 minus I alpha. Now, in order to simplify this a little further, I'm going to multiply by the conjugate, meaning 1 plus I alpha, 1 plus I alpha. And that will give me the real part of, and I'm going to distribute this negative I. So this will be negative I, and then this will be negative I times I alpha, which is going to be negative I squared alpha. Now, remember, I squared is negative 1. So this is really just plus alpha over. And in the bottom, if I FOIL this, this will become 1. And what do I get? Minus I squared alpha squared. Now, once again, I squared is negative 1. So this just becomes plus alpha squared. Now, I'm looking for the real part. So if I were to separate this, this is the real part of negative I over 1 plus alpha squared plus alpha over 1 plus alpha squared. And guess what, guys? We only care for the real part. That's why we've been putting the real part this entire time. So this imaginary portion of our solution can now go away because I'm not interested in that. So right now we have f prime of alpha is equal to alpha over 1 plus alpha squared. And what do we have? We have a function with only alpha. So now we can go ahead and go with our find. We can go ahead and integrate this from 0 to 1 with respect to alpha, and the same side, or the same thing on the right-hand side. We already know this is just f1, which is exactly what we want to find. This over here, if you were to do u substitution, making this your u value, then that's your du. You're going to have 1/2 natural log 1 plus alpha squared, but then we're still integrating from 0 to 1. You go ahead and plug in 1. So you have 1/2 natural log of 1 plus 1 squared, which is just natural log of 2, minus, and then you plug in 0, and you have 1/2 natural log of 1, which is going to be 0. And this will be our solution using the Feynman technique.